Okay, so we're going to continue with supersaturation, which is basically the idea is we want to say kind of if a graph has a lot of edges, then it has a lot of copies of a graph, some graph H. So let's remember this homomorphism density thing. So the homomorphism density of H in G is T HG, which is this thing hom HG divided by number of vertices of G to the number of vertices of H, where the numerator here is the number of homomorphisms from H to G. Where again, a homomorphism is like some kind of edge preserving function. Okay, so last time what we proved was that every graph G, basically we've got this kind of bound, some kind of bound on the number of force cycles in G in terms of the number of edges. Where when I say number of, I mean number of homomorphisms. And today what we're going to do is extend this to any even cycle. So for any k at least 2, what we will prove is that the homomorphism density of C2k in G, so cycle of length 2k, is at least the density, the edge density, so tk2g raised to the power of 2k. Maybe just for context, like let's talk about how this relates to. So this is actually like a special case of like a big conjecture in extremal graph theory. So there's something known as Sidorenko's conjecture. Which says that for any bipartite graph H and any graph G, the homomorphism density of H and G is at least the density of K2 in G raised to the power of the number of edges of H. So like I say, this is it's a big kind of conjecture. It's known to hold for like many different graphs H, like many families of graphs. So we're going to show that it holds for even cycles. It's also known to hold for things like hypercubes and I mean, many different examples of graphs. Families of graphs, but it's still not known in general. So it's an open problem. Before we go into the proof of this theorem, maybe we should give a bit of intuition, like why is this the bound? Like why is it natural to bound the number of copies of H or the homomorphism density in terms of this edge density raised to the power of E of H? And it's natural because there's a kind of a nice kind of tight example for this. Actually, usually the tight examples for the theorems we've been proving were just complete multipartite graphs, so they're super structured. Like you divide the vertices into parts of equal size and you put all the edges between them. An interesting thing about this conjecture is that the the tight examples are actually very unstructured. In fact, they're completely random. So let so for some integer n and some real number p, so let GNP, so where n is a natural number and p is between 0 and 1, be a graph on n vertices where for any distinct pair of vertices, so uv in the vertex set, well, I'll just say distinct vertices u and v, there is an edge from u to v with probability p independent of all other pairs of vertices. So this is something called an Erdős-Rényi random graph. But anyway, so this is kind of a standard random graph. Is it clear what I'm saying here? If you think of p as 1/2, basically for every pair of vertices you flip a coin. If it's heads, you put the edge. If it's tails, you don't put the edge. And you just do that independently for all pairs. So, flip the coin n, choose 2 times. And if you think about it, there are ways to make this more rigorous, but this is not really a probability course. But I'll just say that with high probability, and when I say high probability, I mean the probability goes towards 1 as n goes to infinity. So for any fixed p, so just pick p to be 1/2 and let n go to infinity, you're going to get the density, the K2 density in GNP. If you think about it, it's going to be roughly p. And that's because you're going to get kind of p times n choose 2 edges on average. And this homomorphism density is like the number of edges divided by n squared over 2. And so basically, kind of the n choose 2 and the n squared over 2 kind of cancel in a sense as n goes to infinity. And you're just left with a p. And for any graph h, the homomorphism density of h in G is going to, as n goes to infinity, if you think about it, every edge of h, if I fix a function from the vertices of h to the vertices of this random graph, we're just kind of looking at we're trying to compute the probability that each of those edges of h are present in the random graph. And that's going to be approximately p to the power e of h, number of edges of h. So this gives us an example which is, at least as n goes to infinity, it's kind of asymptotically tight for this conjecture, because this side would be p to the power of e of h, and this side would also be p to the power of e of h, right? Because plug in a p there, it has the right power, and then this is just p to the e of h here. So it's not exactly tight for any given choice of n, but as n goes to infinity, it gets closer and closer to being both sides of the inequality being equal. Any questions about that? But this is all kind of just a bit of extra context for why it's kind of natural to prove something like this. And so now let's just focus on proving this theorem. So something I like about this proof is that, so last time when we did this thing about C4, all we really did was apply this convexity of, like kind of basically Jensen's inequality or Cauchy-Schwarz or whatever you want to call it. We applied this thing about sums of squares twice, and that was the whole proof. This proof is going to have nothing to do with that. Like there's going to be, in some sense, my feeling is that the proof we're going to give today has really kind of no real similarity to this one. So we're going to use linear algebra to prove this. Okay, so the first thing I need is to introduce the adjacency matrix of a graph. So if G is a graph with, let's say, vertices V1 up to Vn, the adjacency matrix of G is the n by n matrix that I'll denote by A sub G, where the ij entry is 1 if vi, vj is an edge of G, and 0 otherwise. Okay. Strictly speaking, this matrix is not really just depending on G. It's also depending on the vertex labeling, right? Because if I label the vertices differently, I'll get a different matrix. But for all intents and purposes, it doesn't really matter. I mean, all the properties of this matrix that we're going to use are independent of the ordering. So yeah, so just order your vertices however you want, really. As an example, if G is this graph, let's say I label the vertices V1, V2, V3, then the adjacency matrix is going to be, so V1 is adjacent to, not adjacent to itself, it's adjacent to, so this row is for V1, V2, V3. So basically you've got one row and one column for each vertex, and you have to do the same kind of ordering of the rows as you do for the columns. And if we fill this in, so V2 is adjacent to everybody but itself. V1 is only adjacent to V2. V3 is also only adjacent to V2. So it's like 0, 1, 0, 1, 0, 1, 0, 1, 0. Okay, so here's a nice thing about the adjacency matrix. If I take powers of the adjacency matrix, it gives me a lot of information about the graph in terms of like how many walks of a certain length there are from one vertex to another. So I claim that for any kind of integer L at least 1, the ij entry of the nth power, so when I'm saying the nth power, I'm just applying matrix multiplication, you know, over and over, counts, so is equal to the number of walks of length L from Vi to Vj. And just, okay, so this is, might not seem super relevant at the moment, but just to give you an idea of where this is going, like if I know the number of walks of any length from one vertex to another, in particular, I know how many walks of, let's say, length 2k there are from a vertex to itself. And then if you think about it, oh, what is a walk of length 2k from a vertex to itself? It's just that is what a homomorphism of a cycle of length 2k is. It's just like if I pick that vertex as being vertex 1 of the cycle, then the next vertex has to be adjacent to it, and so on and so forth. But literally, that's just what it is to take a walk from that vertex to itself. So counting these walks is going to count homomorphisms of cycles. As long as, if you start and end at the same place, that's a homomorphism of a cycle. Okay, so the proof of this is pretty easy. We're going to go by induction on L. So the kind of basis case, L is equal to 1. And then we just kind of think, oh, how many walks of length 1 are there from some vertex to another one? If there's an edge there, there's one walk, because you just have to go along that edge. If there's no edge, there's no walk of length 1. So the case L equals 1 is, so there's one walk from Vi to Vj of length 1 if Vi, Vj is an edge, and 0 otherwise. And this is, so therefore the adjacency matrix kind of encapsulates walks of length 1, right? So now suppose L is at least 2. And basically, this now just comes down to, do you remember how matrix multiplication works, basically? So if I take, so the ij entry of A to the adjacency matrix to the L is equal to, well, the sum overall k from 1 to n. I take so I'm going to think of the adjacency matrix to the L as being the adjacency matrix to the power L minus 1 times the adjacency matrix. To compute a matrix multiplication, I take like the first row of this matrix times the first column of that matrix, and so on. So I'm going to go through each column of, so I'm on the, how does this work? So I'm going to go through the ith row of this matrix. And go through all possible choices of k, and then go through the jth. So all possible choices of k and the jth column of that matrix. That's how matrix multiplication works, right? These things should kind of match up, and yeah, so anyway, this is the ij entry of the matrix. And then we just kind of use induction. We say, oh, that's the number of walks of length L minus 1 from I to Vi to Vk. And this is the number of walks of length 1 from Vk to Vj. How do I get a walk of length L from Vi to Vj? I walk L minus 1 steps to something, and then I take one step to the last step from that something to Vj. So yeah, this is equal to sum over all k, number, so by induction, number of walks of length L minus 1 from Vi to Vk times number of walks of length 1, which is, walk of length 1 is just an edge again, right? So, but anyway, I'll write it like this. So walks of length 1, sorry, this is really messy, but from, oh, sorry, this was supposed to be to Vk. So Vi to Vk, and then Vk to Vj, which of course the number of walks of length 1 is either 0 or 1, depending on if there's an edge. But this like exactly counts the walks of length L from Vi to Vj, right? Because you go Vi to somewhere, and then somewhere to Vj, and we're summing over all the possible kind of second to last vertices. So yeah. So basically this is what we wanted. So I'll just write what we wanted. Okay. Okay, so so like I was saying, I mean, to be honest, I don't really care about the number of walks between every vertex and every other vertex. But what I do care about for counting cycles is walks that start and end at the same place, because that's literally a homomorphism of a cycle. So just to remind you about something called the trace of a matrix. The trace of a matrix is the sum of the diagonal entries. So the trace, let's say TR of B of a square matrix B is the sum of the diagonal entries and basically a corollary of this claim is that the number of homomorphisms of a cycle of length 2k, or let's just even say, well, any length, let's say L, to G is equal to the trace of the Lth power of the adjacency matrix of G for any L where this makes sense. So cycles can have length at most, or at least they have to have length at least 3. So yeah. Right, and this is just what I said. This is counting homomorphisms of a cycle is just, so any given diagonal entry counts the homomorphisms where the first vertex of the cycle, whatever that is, maps to that vertex. And then we just sum over all the possible choices of the first vertex. Okay. So let's prove this theorem now. Along the way, we're gonna need some facts from linear algebra, but I'll just kind of state them as we go. So yeah, let G be a graph with n vertices. Well, so one nice thing about graphs is if I take their adjacency matrix, it's always symmetric because Vi is adjacent to Vj if and only if Vj is adjacent to Vi, right? So, so note that the adjacency matrix of G is symmetric, meaning that the transpose of the adjacency matrix is equal to the adjacency matrix. And I guess recall from linear algebra, or if you don't remember this from linear algebra, just learn it for the first time. I mean, it doesn't really matter. That any symmetric matrix, so symmetric just means this transpose condition. The transpose is equal to the matrix. Any symmetric matrix over the reals. So, of course, the entries here are real numbers. They're 0 or 1. Has, well, symmetric n by n matrix has n real eigenvalues. They may not be distinct, right? So you can have the same eigenvalue many times. So basically we can let lambda 1 up to lambda n be the eigenvalues of the adjacency matrix of G, where I'm going to assume lambda 1 is at least lambda 2. So we can just put them in order. And yeah, like I said, some of these can be equal to each other, but it doesn't matter, right? So like generally a matrix could have, in some sense a matrix always has, an n by n matrix always has n eigenvalues, but the special thing here is that these ones are real, right? Generally you could have complex eigenvalues for a real matrix. Okay, so we're counting cycles of length 2k in G, and we've shown that this is equal to the trace of the 2kth power of the adjacency matrix. Does anyone remember any kind of connection between the trace and eigenvalues or anything like that? Oh, sorry? Exactly, yeah. So yeah, this is going to be equal to the sum of the eigenvalues of this 2kth power of the matrix. But if you think about, maybe I should remind you what an eigenvalue is, right? But so just as a side note, if you've forgotten this, so lambda is an eigenvalue for matrix A if there exists a non-zero vector such that, so non-zero vector x such that A times x equals lambda times x. If I know the eigenvalues of a matrix A, though, it's kind of easy to see what the eigenvalues of the kth of a power of A will be, because basically, if you just take the same vector x and apply A many, many times, kind of by linearity and stuff like that, you'll just get lambda to that power here. So the eigenvalues of this kth power are the 2kth power of the eigenvalues of the adjacency matrix of G, and like you said, the trace is the sum of the eigenvalues. So this should be, the trace is equal to the sum of the eigenvalues of the 2kth power, which are the 2kth powers of the eigenvalues of the original matrix. So we just define these to be the eigenvalues. We don't know what they are yet. But yeah, so this is a general fact. The trace is equal to the sum of the eigenvalues. Now let me do something that looks so extremely wasteful that there's no way that this could possibly lead to anything, to any kind of like a tight bound like we're aiming for. So this is a sum of like n different things. I'm just going to take the biggest one. That's all. We're going to ignore every single other term. So this is at least, it's important, so this is at least lambda 1 to the power 2k. Now here it's important that these eigenvalues are real, right? Because if I had like I in my list of eigenvalues, then I take the 2kth power, it'll be -1. So, right? So all of the terms here are non-negative because these are real numbers. So this is because lambda I is real for all I. Okay, so if the matrix wasn't symmetric, I would have, this would have messed me up, right? But since these are real eigenvalues, I can do this. And yeah, it seems insane that this is going to work. We're just wasting all of the other eigenvalues, not even using them. So I need to bound lambda 1. And then if I can bound lambda 1 in terms of the number of edges, then we're going to be able to like divide this by n to the 2k and hopefully get the bound that we wanted. So let's just bound lambda 1. And here's another fact from linear algebra. So recall, or like I said, possibly learn for the first time, but either way it's fine, that the largest eigenvalue is, so I mean, can be computed by the following following formula. So lambda 1. So lambda 1 is the biggest eigenvalue. That's how we defined it. And this is the max over all non-zero vectors. I don't know if I should put a little vector thingy on this. Maybe I'll start doing that. Just to make it clear, this is not a, this is a vector. And then I take the dot product, or the inner product, whatever, I mean, that's, dot product of x. So we're specifically talking about this adjacency matrix, but this holds for, I guess, at least any symmetric matrix. And then you divide by the dot product of x with itself. Okay. So in principle, if I wanted to determine this exactly, I could find this maximum, maybe. I mean, but I don't actually really care about getting exactly what the maximum is. I mean, the nice thing about this is that this gives me a way of certifying a lower, like all I need on lambda 1 is a lower bound, right? This gives me a way of kind of probing and trying to get a lower bound on this lambda 1, because if I plug in any x, and I just compute this number, well, that number will be a lower bound for the maximum, right? So if I put in any x, you'll get something, any x non-zero, you'll get something here which will lower bound your lambda 1. It might not be the best possible choice, but it'll give you some bound, right? So, so basically we just have to try something that is hopefully going to work. And it turns out for this proof, what works is just take the all 1s vector. So, so I'm going to take the all 1s vector, and then I'm going to take the all 2s vector. So this is the all 1s vector. So this is the all 2s 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 So consider x to be the all ones vector in Rn. So let's first think about what is Ag times x going to be. So this is going to be some kind of column vector, I guess. Yeah, I think so. Of length n. Can anyone tell what the entries are going to be? Yeah, exactly. So I've labeled my vertices v1 up to vn or something. So like, yeah, the first entry is going to be the degree of v1, the degree of v2, down to the degree of vn. Right? Because if I think about it, take the first row of this adjacency matrix and multiply each entry by 1. That just adds up it just sums the row. The sum of each row is the degree of that vertex. So this is quite nice because if I take this dot product, remember this is the all ones vector, that's just going to sum my degrees, and I know what that is. So this is the sum of the degrees, which is just 2 times the number of edges. I feel like every day we relearn the handshaking theorem again, right? It's like every single time it's just handshaking. Anyway, the dot product of x with itself, of course, it's going to be n. So what I get is that, so anyway, this is what we're trying to prove, right? So what I get is that lambda 1 is at least 2 times the number of edges over n, which is like pretty much, it's quite similar to this, what do you call it, the homomorphism density. It's just like there's an n missing on the bottom. So this is like literally equal to n times this tk2g thing. Right? Because the numerator actually counts homomorphisms from k2 to g. It's 2 times the number of edges. The denominator, it should be n squared. So that's why I've got an extra n here, right? It'll cancel and yeah. So therefore, what I've got is that this c2k g, which is number of homomorphisms of c2k to g over n to the 2k, is at least lambda 1 to the 2k over n to the 2k, which we've said is at least n times the k2 density of g to the 2k over n to the 2k. And the n's cancel. Okay. So yeah, this implies what we did, one of the things we did last time at the end of class, this thing about even C4. And somehow somehow like the proof, I don't think this has, okay, except for the fact that we used handshaking. Like there's pretty much nothing in common with the other proof, which I think is nice. You could like try to apply the ideas in the other proof to get this same theorem, but I think you'll be stuck. Like, for example, just to get the result for, like I think you will probably be able to get some even cycles that way by just doing kind of a sum of squares argument. But like I think a 6th cycle, you'll be stuck. And so this kind of spectral approach is useful for that. Yeah.
Does this fail for odd cycles?
That's a good question. So it fails right here because these eigenvalues are still real, no problem with that, except that they can be negative numbers. And so if I take a negative number to an odd power, it'll be negative, and so there's going to be cancellation within this. Whereas, yeah, I guess I'm using that these are real numbers and the exponent is even. So they're all non-negative. So maybe I'll just like give a couple of seconds of intuition about, like this step here did feel like when we did it, I was trying to convey that it's a little bit surprising because it looks like so extremely wasteful to just care about the biggest eigenvalue. But then if you think about our tight construction was a random graph, right? Imagine I've got a big matrix of ones and zeros, and I put the ones and zeros kind of randomly in there. So that matrix, it's going to probably, okay. Like the thing is, eigenvalues kind of indicate some kind of correlation with some vector or something like that. The thing is, if I take a random matrix, it's going to have one big eigenvalue. Essentially, a big random matrix is essentially flat in some sense. If I gave you, for example, if I did a random graph with density 1, the matrix it'd be the complete graph. Okay, you'd have some zeros on the diagonal, but everything else is a 1, right? As n goes to infinity, this matrix is practically just flat. It's just ones everywhere. A matrix with just ones everywhere, it has one eigenvalue that's non-zero, and the rest are all 0. So like in some sense, because our tight example is a random matrix, there is going to be one dominant eigenvalue, and the rest of the eigenvalues, they're not 0, but they're pretty close. I mean, they're dominated by the biggest one. So in some sense, this wasn't such a big throwaway because the tight example really does have one dominant eigenvalue. But anyway, you don't really need to know any of that philosophy. Any questions about any of this? Okay, so next time we'll do some more general supersaturation for any graph H. And then I think we'll move on to a slightly different topic.